All right, I'm going to go ahead and get started again. Everybody gets a peek backstage. There were no other questions during the break, so again, if you have them as you think of them, put them in the channel. All right, so how many people are back in? All right, looks like I think everybody's here. So sort of part two. So if we open the part2.html, that's what we're going to be working on now. You don't have to like restart R or anything like that. In fact, we'll be reusing the AIMS data, so that it'd be good to have that available. The focus of this section is going to be on how we use our data. So I kind of alluded to this in like one of the last slides. Like what we're going to do is, if you've never done much machine learning, we sometimes allocate data to be used for specific tasks. So we're going to talk about how to do that. And this will not be a long section, so you might be able to get through it today. So there's this idea of data splitting and spending. So over the years, there's been, I don't want to say controversy, but it's been discussed quite a bit. There's a bunch of ways to spend your data. So, and this comes also into play when you have big data, like large amounts of data. I think the one thing that I would suspect most people would agree on is we don't want to take all of our data and just build models on it, right? So I hear that a lot where people say like, oh, I have this database, it's like 3 terabytes of data and I want to build my random forest model on that. I'm like, oh God, like maybe don't do that. And not necessarily related to anything that's a limitation or anything of R, but what we definitely want to do at the very minimum is to have a separate data set that we hold back. And then that data set is used at the very end and only to measure performance. So, and that is typically called the test set. So the most basic delineation or splitting of data that people typically do, and I would say in the majority of modeling cases, is they take their data and split it into 2 different sections. So the training set is used to do, it's like your playground. It's like your sandbox. So it's where you estimate your parameters, compare models, tune models and things like that. It's the majority of the data that you're going to use for building models. And then the other data set typically is the test set. And the test set is only used at the very, very end when you have 1 or maybe 2 models that you want to get a final sort of bake off on. You want to say, well, okay, which one of these models is best performance-wise on a separate data set? And the idea of the test set is to have a data set that's completely independent of all the modeling that you did. So it's really like a blinded or really unbiased arbiter of how well your data works, because it was not used in any other context besides evaluating the data. So you almost never look at the test data more than once or twice. And then there's a bunch of other ways to split your data. There's validation sets, and we'll talk about resampling and things like that in a little bit. This is what you would use in most situations. So we'll talk a little bit about the mechanics of doing a data split. So we're going to take our data set, in the AIMS data, we have like just shy of 3,000 properties, and we want to take some of that data and put it in a test set, and let's say the remainder and include it in the training set. So how would we actually do that? So the simplest thing you could do is just like basic, simple, random sampling, right? You just randomly allocate some percentage of data. Let's just say for kicks right now, 20%. So let's say we're going to take 20% of our data and put it in the test set and 80% of it in training. I'll talk about that fraction in a minute also. How would we actually do that? What you could do is you could just select 20% at random. And that works most, in a lot of cases, but it really breaks down in other cases. So imagine a data set where you have like 2 classes, and one of those classes has like a 3% event rate. So simple random sampling, especially if you don't have a lot of data, is problematic because you might get like 1% of those events in the training set and 5% of them in the test set and so on. So the thing that we probably do most often is something called stratified random sampling. So in the case of classification, what you would do in this example scenario I just gave you, is you would take that 3% of the events and you would do an 80-20 split of those data. You would take the majority non-event data, do the same 80-20 random split on them, and then you combine the two like sub test sets and the two sub training sets. So by doing the splitting within class for classification data, we ensure that the event rates between training and test are pretty much the same. If you have small data sets, they might be off by a little bit, but that's probably as good as you can get. There's never been any proven downside of stratified sampling. This has been studied back in like the 80s and 90s when it was first proposed, and I've never seen any evidence that it's ever done any harm to a model or to an analysis. So it's the kind of thing where there's very little to worry about in doing that. How would you do it with non-classification data set? What we typically do is we take the data and we take the outcome data and split it into quartiles, and then do the splitting inside of those quartiles. So the 25% largest, let's say, sale prices names, we would take those data and do an 80-20 split, and then do the same thing with the lowest 25%, and then the two sets of 25% in between, and then pull those data into our overall test set and training set. So I think I have no, I don't have a graph here. This is something that Carrot defaults to. As you'll see in a minute, the tidymodels don't default to do this, but it's very easy to do stratified sampling. So this is what I typically advocate people do, because again, it solves more problems. It doesn't really create any. So the package within tidymodels that's automatically loaded with the tidymodels package is called RSample, and that's the one that is what we use for resampling, and it has like the data splitting type functions in it. So you can see the little boot up here. We're, for this data set, are going to put 3/4 of data into training and then 25% into testing. So at this point is normally when somebody says, well, why did you pick that percentage? This is sort of like my baseline feeling about what that split should be. So I would say at least 50% of the time, this is what I would use. The other 50% is really based on characteristics of the data. It really depends on your data and your situation and what you're trying to do. If you have a lot of predictors relative to the number of data points, I might do something different. If you have a lot of classes, like a 10 class problem, I would probably maybe adjust that compared to like a 2 class problem. So it's really hard to explain and to come up with like a general rule for this. It really depends. The thing is, if you have a lot of data, it doesn't really matter. I mean, to be honest with you, you have like 5 million data points. It doesn't matter whether you do 50 or 25%. There's at some point where you have enough data where adding more data will not change the model at all. That amount of data depends on the problem and the model you're using and things like that. But if you have a lot of data, it's really, this choice of training and test is really, really insensitive. You don't have to sweat it too much. For small data sets, it does really matter. But then there's things like the event rate and other aspects that I think for me would really drive that decision. I've had the example that I use as an extreme case is I had a problem one time with 110 data points, about 8,000 predictors, and they were very highly correlated, and like 7 or 8 classes. So I have 110 data points in 7 or 8 classes. Some classes only had 2 data points in them. So it was a really problematic question because, if I allocate data, do I take like, if class A had 2 data points out of 110, do I put like 1 in training and 1 in testing? What does that do, right? Or, it wouldn't make sense to put them in testing because you don't have any data that would ever be used to predict them as that class. So it can get really complicated. In that particular problem, what I did is the scientist inside of me wants to always have a second data set, like a test set to validate my model. Even if it's a really bad data set, I feel like I really want something that will give me even a gross estimate of performance. So what we did was we took the classes that had the most data and took 10 of those out of 110 and put those into a test set. We knew it was not a very good test set, but it was better than nothing. And then we trained the model on the 100. That 100 included all the really small classes too, that had like 1 or 2 or 2 or 3 data points in them. And here was our reasoning, is that feature selection is really, really hard to do without overfitting, especially when you have a little bit of data. So probably the most difficult situations I've ever been in modeling is when you have 100 data points, but thousands and thousands of predictors. The chance that one of those predictors is accidentally going to split the data in the training set can actually get kind of high. So it's really, the thing you want to worry about is having something that looks good on your training set, but doesn't repeat in new data. And that's the definition of overfitting. And when you have a really big, really small number of rows, but very big number of columns, if you just do the math, the probability that that's going to happen becomes larger and larger. So with this particular example, we had so many predictors, we were worried about making a mistake in the training set and not having data in the test set to diagnose that, even at a gross level. And that was the main reason. I guess the only thing I'll say is, like, there are some statisticians that feel like the resampling methods we'll talk about a little bit tomorrow, or tomorrow probably, are really good at getting estimates of performance from the training set, but it is possible you could do those incorrectly, and I have done that. There are some subtle things about resampling that, at least when I first started doing this stuff, I made mistakes, and I did not know it until I saw a test set or like new samples. So for me, I get really paranoid about this, and I want to have a data set that will tell me if I made that mistake. So I think paranoia is a good thing here, and that's why I always have a test set, even if it's something that is suboptimal at best. Okay, so how do we actually do this? Back to reality, how would we do this? If we have our AIMS data, what we can do is the RSample package has something called initial split, and that will give us the information that we need to split the data into training and test. So what we do is initial split uses random numbers. So if you've never seen this before, what we do is we set the random number seed to just some integer that pops into our head. Maybe use the hour, like right now I'm on the East Coast, so I would maybe use like 341 or something as my seed. It just needs to be something that will make sure that you can reproduce the random numbers that you use in your analysis. And so if I run set seed and then this data split, every time I run this in the future on another computer or 10 months from now, I always get the same splits because I fix sort of like the random number stream. So what initial split does is it looks at your data. I told it to stratify by sale price. So internally, what this function is going to do is it's going to do the 75%, 25% split. That's the default. We can change that by adding another argument. But it will do that within the quartiles of the data. And then the result of this function is to give you an object back that has the row assignments. So initial split doesn't do the actual split. It gives you like the information about which row is going to training and which row is going to testing. So once you have this object, we have these convenient functions called training and testing that when I run training on the split object, it gives me back the data frame of the original data. So AIMS train here is a subset of AIMS that has the 75% rows that go in the training set. And then similarly, AIMS test uses the test function, and that gives us back the rows that are supposed to go into the test set. So these are two data frames or two tables that look exactly like the original one, but they just have different rows in them. So all the columns are the same, but this has, I forget what the number of rows is. But you can see when I do the ratio of these things, the training set is 75% of the overall. So if I didn't include the strata here, it would just do random sampling. But this is how you would do stratified sampling. So now when we do all our model development, we're going to use this training set. for illustration, we are going to use the test set, but as you'll see in the notes, we really, really want to discourage people from just using it whenever they want to use it, because if you keep looking at the test set during development, it's not a test set anymore. It's part of the development process. So we don't want to, in reality, like in practice, we don't want to use this at all. In fact, in my last job, what we would do is we would have a third party, somebody who was not in our group, do this training and test set split. And then what we would do is we would have them for the testing data not give us the outcome data. So there was no way that we could actually make predictions on the test set until the very, very end. That may seem like paranoia, and just to be honest, it was. We had the problem of, how should I say this, our management frequently giving the same data sets to outside collaborators who maybe don't know anything about machine learning but knew how to use software. And we had a lot of instances where, our leadership would come back and say, I don't know what you're talking about. This external collaborator biologist got like 100% accuracy. Like, why are you at 80%? And we're like, did they predict the test set? And he's like, yeah. I'm like, well, if they use it, I can get 100% accuracy if I include the test set in the training. So, so we became kind of paranoid that we weren't sure who was going to have access to the data, and we wanted to make sure everybody was constrained to use a good methodology. And that methodology includes don't look at your test set until the very end. So if you're in that situation, that might be a good thing to do. And I wouldn't be surprised if a lot of you are like, wow, that's paranoid, but it's kind of where we were. Question is, can you comment on the difference between initial split and create data partition from Caret? They're basically the same thing. The mechanics under the hood are different. Create data partition basically gives you a vector. I think it gives you back a list or a vector of integers. Initial split is a little bit more complicated of a data structure with a class to it. But for all intents and purposes, one initial split is just a re-implementation of create data partition. So there's really not much else to it. You won't get the same numbers because the implementations are different, but their specification of what they do is the same. One other aspect of that is, I believe RSample has functions called caret to RSample and RSample to caret that I think would work. They're mostly written for the resampling stuff, but I think could be used if you want to go between formats. I haven't tried that with initial split, but it should work fine. Yeah. I'm going to pause for a second because people are typing. Okay. Large data sets slow down my progress. Is there any good way to identify what is the sufficient sample size for data I'm using and the problem I'm exploring? Yes, there is something called a learning curve. And so what a learning curve is what you can do some initial, you do some initial work to figure out, like imagine this like sigmoidal curve when, if you have a little bit of data, like on one axis is the percentage of the training of all of your data, like training and test, like the initial data set you have, the percentages on the x-axis, and imagine the performance of your model on the y-axis. And so when you start adding a little bit of data from almost nothing, you have huge increases in performance. So it's like actually it looks more like a logarithmic curve that, a little bit of training set data has a big improvement of performance, but there is like an asymptote there that at some point adding more data is not the solution. It's capping off performance. For models that I dealt with back at my last job, a lot of them were about 250,000 data points. Like we knew if we added, 500,000 data points, our results were going to be just as good as they were with 250,000 data points. So what you can do is you can do like a little bit of kind of a simulation, like randomly sample like 25% of your total data, fit whatever model you want like once and get performance on that, and then double that and see if the performance doubles. And then, and maybe try like a sequence of 5 or 6 data set sizes and track how performance changes and see maybe where you are on that curve to know whether like it's 1 million data points or 2 million data points or so on. let's see, let me read this. Okay, I'll get to the second question. So for Hunter, hopefully I've answered your question about like I have a lot of data and it slows me down. Okay, hopefully I won't babble about this too much, but one other thing that I tell people when they have very large amounts of data, especially if you have a very rare event rate, is if it's a brand new problem that you're working on and you're like, well, I don't know anything about this data. I don't know what's important to the model, what's not important to the model. When I've been in situations where I have a lot of data, I will take, let's say, like 25% at the beginning and just do data analysis to figure out feature selection. So like what you might do is for things that are potentially problematic in the analysis, take a chunk of data, do that part of the analysis, and then throw that data away. So you never use it again. And that sounds weird, but what's really important is you have all these tasks that you're trying to do in data analysis, and the more you reuse the same data set for multiple tasks, the more likely you are to accidentally overfit. So like data reusage for all these steps can be really, really problematic. So what you can do sometimes is you might say like, wow, I don't know what predictors to use, so I'm going to take some of this data because I have a lot of it, do my analysis to see what's important, and then just throw that data away, but take that predictor set I have, and then now use that in the modeling process, as opposed to some really complicated like feature selection thing. So think about things that are particularly problematic that you can envision and take data specifically for that if you have a lot of it, and then just keep whittling that away and make sure you have enough data to fit the model. But you can kind of compartmentalize where the data impacts the analysis. That's a good thing to do when you have a lot of data. Can you use the same idea, use proportional data in tune with hyperparameter tuning? Yes, we'll talk about that. I'll remember that. We'll probably talk about that on day 3, how data gets used and potentially reused during tuning. Yeah, I'll make a point to bring that up again. Okay, then another question. Initial training set is essential in measuring performance. In your example of your experience, was the split just determined completely before the modeling process and never changed? What if your random training split is just fantastic, horrible? Oh, yeah. I can't think of any occasion where we've gone back and redone it. So I'll qualify that in a minute. I have had situations where all of our evidence said that model X was going to be really good. Like everything we did, we like really rigorously created the model, we resampled it really well, we did all this stuff, and then performance on the test set was not great. I've had 1 or 2 situations where the training set didn't look that spectacular, but the test set did. In those cases, like we worry about like, did we just have like a random bad roll of the dice when we created the initial split? I've never gone back and redone it because at that point, like you can't unlearn the things you learned, and then once you start putting some data in the test set and take some of the training set out and putting it in the test set, like once you start exchanging them and redo the split, then I worry about the bias creeping in. The thing we've done in those cases, and I should say in these cases, we were always accruing more data. So like if we waited a month, we'd have another like 200 data points. And so in those cases, what we did is we said, well, let's maybe not publish the model internally, but let's just get more data as like a third sort of like opinion about what was going on here. And so that's not happened hardly ever to me. I've almost always had the resampling results correlate with the test set, but it has happened in that case. We didn't go back and redo everything. We just sort of said like, well, let's get a little bit more data and have like a second test set that hopefully will tell us which one of these 2 pieces is the right one, to be honest with you. The caveat to that is the only time that we've sort of redone things is related to model updating. So this is kind of a separate question, and it's something in RStudio that we've been thinking about, like how to do model updating. So model updating is like, your job is to build this model, and we're always getting new data. And so you build a model, you publish it internally, the people who use the model use it, but after 6 months, maybe you have like another 1,000 data points. So the question was always like, when do we retrain? Do we just refit the same model? Do we like do a complete retraining and look and see what works and what doesn't? And in those cases, we would have kind of like a new data set, and we would do another training test set split. So that's not probably exactly what the question was, but that is an instance where we had to plan forward on how we're going to use new data when it comes in, and we have the answers to the outcomes. So that's just, if you're in that situation, maybe contact us, because like I know what I've done in the past, and we're thinking about how we can do that with our software, and what are good practices, because a lot of people have things they do in-house and everybody's different. So model updating is an interesting question, and we're thinking about that a lot. Let's see, with new data coming in, do you use all that as test set or split again, training and test sets? Yeah, so that's what I'm talking about. So what we would do, we had a lot of data that was not time sensitive, but so I was working in drug discovery in computational chemistry, and what would happen is the way chemists make potential drug candidates changes a lot. So data that we had like 2 years ago may not be really the same type of data that we were getting now. So the potential drugs people were designing, let's say in 2018, if I were still doing that job, would kind of look really different than the drugs that they're designing in 2020. And so we had this sort of system of like rolling training test sets that even if our database had like 1 million data points in it we could use for modeling, we did some learning curve stuff and figured out, let's say that 250,000 is always like the tipping point where adding more doesn't really help. So we would take the most recent, let's say 1,000 data points as our test set. And then we would take after that the most recent 250,000 as our training set. And so when we retrained and all that, we would have like a moving sort of training and test set that we would do. And then there was a lot of data that we just didn't want to use anymore because we didn't feel like it was relevant, because the kind of things that people were designing in like 2015 didn't really make sense for what we were doing. It was actually quite more complicated than that, but that's the gist of it, is we were very particular about what data went into the model. And since time was important, we wanted to bias ourselves towards more recent data than a random sample of everything back to the 80s or whatever time frame it was. Yeah. So I'm working with data spread out over a couple of years. I always try to use out of time test set. Is that necessary? Is there a good way to know whether it's needed? Maybe if you could write, what do you mean by out of time? Do you mean like the most recent data? Okay, yes. So yeah, for the stuff that I was working on, we had a lot of discussions about this. We thought there's good and bad. So we thought the most recent data set was the most relevant for predicting performance of the model. Universally, everybody thought like that's a good idea. But then a lot of the people who did modeling, we were like, well, okay, the problem with that is our performance of the model it has a random component. So if you're a chemist and you're working on a project and let's say you're going to design like 250 drugs to test to see if they work, what if you do a bad job that week, right? So let's say like none of them work, right? So the distribution of the data that is your test set for that period is in one part of that outcome distribution, right? So imagine like with the AIM sale prices, let's say we're always getting new houses on the market, but something happened where like one of our rolling test sets was like in the really really high, really expensive houses, right? So the problem with doing like using the most recent data all the time as your test set is is there's variation there that's unrelated to the model. You're sampling from different parts of that distribution, and if it gets concentrated in one area, it's like you can't, if your accuracy is like 80%, well, that might not be like the same 80% as we had last week, because there were different data that went into that. So the other thing we did for some projects was we found data that we thought were historical data that weren't going to change, but they were representative of the whole of our data that we wanted to predict on. So we basically went back and found like a challenge set that was like a static test set, like a second test set that was always the same. And we thought that the data that went into that was good data in the sense of like, yeah, those are things we'd always want to try to predict well. So we had like a moving dynamic data set, which was like the most recent data. And then we had like a specific like static data set that was always the same. And so if the dynamic most recent data really tanked or did especially well, we could balance that against, well, what does this model still do on these data that have always been predicted? So there's different things and strategies you can do to solve that. Yeah, it's kind of hard to do. Luckily, again, where I worked, we had a lot of data, so we had a lot of like freedom and things to do this. But when you don't have a lot of data, that's the really hard part. So yeah, if you have more questions about this, think about it, and maybe in between sessions, like if you have more details or more specific thoughts, please put them in the general channel. Normally, this is the kind of stuff we would talk about at lunch during an in-person workshop. So I'm happy to answer these questions as much as I can. Okay. So, all right. So this is how functionally, like, we would make a simple training test set split. And again, we use this initial split to get the row assignments and then these convenience functions to tell us what's training, what's testing. So a little bit about this, if we take that data split object, the one that came out of initial split, and we just print it, we get this thing that looks like this. It says analysis assess total. And what these three numbers are, this third number is the total number of data that we had originally. So AIMS, that original data frame, has 2,930 properties. And with this particular split, the data is going to be used for modeling is just shy of 2,200, and 731 will be our test set. So this just gives you a breakdown of what the split was. And again, just showing you that the training set looks like the AIMS data. Same number of columns, just different number of rows. All right, so let's talk about modeling. This is going to start off as like base R modeling, and then we'll get into tidymodels approaches. I sort of said this earlier, that there's really two sort of classes of interfaces for models. The first one's the formula method. So if you click on this link, it'll take you to the core R documentation about how to make formulas. But the gist of it is, using the formula method, is you have some modeling function, I don't know, it's random forest or KNN or whatever, and then you give it a specification of variables. And so sale price tilde neighborhood plus year sold plus neighborhood colon year sold. What this means is sale price is going to be our outcome. Neighborhood, which again is a factor column, is going to be a predictor. Year sold is a numeric column, that's also going to be a predictor. And then this is, we'll talk about interaction effects later. This is an interaction effect between neighborhood and year sold. So in linear regression, what this would mean is that you would have potentially different slopes and intercepts for year sold per neighborhood. If you didn't have this in here, if you didn't have this term in here, what you would have is all the year sold slopes would be the same over neighborhoods, but their intercepts would be different. So this what means that there's a variable interaction between these two predictors. The relevant things to realize about this particular formula is it's doing a few things. This has come up quite a bit recently in the things that we're working on in the tidymodels group. It's saying that sale price is our outcome, neighborhood and year sold are our predictors. So it's like kind of assigning roles of like how the data are going to be used. Whether you realize it or not, initially, neighborhood is a factor. And many, in most, in fact, modeling methods like linear regression can take a non-numeric output and use it in modeling. So what the formula method would do, and we'll talk about the exceptions to this, 99% of the time, the formula method would say, oh, neighborhood is not numbers, so I'm going to find a way to encode it into numbers. And we'll talk about dummy variables later, but there's, I think, 28 neighborhoods in this data set. So what it would do is it would remove neighborhood from the data that goes into the model and replace it with 27 new columns that are 0 or 1 depending on what neighborhood you're in. So it substitutes this original column with an expanded set of numeric columns that can be used for modeling. So that's another thing the formula method automatically does for you. The third thing it would do is when it makes these interaction columns, not only would it encode neighborhood into dummy variables, it would multiply those dummy variables by year sold to make an additional 27 columns in the data set. So it's doing a variety of things. It's saying like which variables are used for the outcomes, which are predictors. So that's the roles. It's in handling how data are encoded. Like neighborhood should not be given to the model as character or factor. It should be made into numbers. So it's doing a variety of different things in one sort of like line of code. We'll talk about this more as we go on. When you have the formula method, it also has to be accompanied by, usually it's called data argument, which is a data frame that would be needed to find these particular columns. Now, let's say you have thousands of predictors. Well, you don't want to have to type those out. So the shortcut is the dot. So in this particular interface with the formula, what it's saying is sale price is the outcome. Everything else in this data frame that's not sale price is a predictor. So it's shorthand for all predictors. And there's some things you can do with the dot, like in terms of like interactions and things like that. But basically this represents everything that's not on the left side of the tilde here. Another really great thing you can do with it is you can do inline functions. So we're going to model sale price on the log scale. So I can just type in log 10 here and it automatically logs the data before it gives it to the model. You can also do things like, this is a spline term, a natural spline. If you've ever used GeoSmooth, like those smooth terms, or using usually either something called LOS or splines. And so what this would do is it would take the longitude column and substitute it with 3 different columns that allow you to model longitude non-linearly. So I don't want to focus on like how splines work. The point of what I'm saying is I can make inline functions here on either side of the tilde to do data manipulation and things on specific columns in my data set. So you can inline functions with the formula. There's some limitations to that, but it's very, very, very convenient. The other thing that it does that may not be obvious to this is when you use a formula method in some inline function, let's say inline functions on the predictors, when you go to make new predictions, it applies these same transformations to new data. So if you make splines using this particular formula, you don't have to manually make those spline terms when you make predictions. These transformations of the predictors are sort of embedded in the model. So when new data is given to the model, you just give it longitude, and it does the same transformations it did before. So model function here is just a placeholder. It's just to represent whatever model you're using, like a Ranger or LM or whatever. So this is just like a generic like foo or some modeling function. It's not meant to be literal. So. I'll go on. So the formula method is really convenient. It's just it's been around in S since like the early 80s. It was a kind of a blessing when we first had it available and started using it. There's some downsides though. Like you can't inline multiple things. Like if you want to center and scale your data and give it to PCA, you can't really do this. It happens on a predictor by predictor basis for the most part. And so that's a limitation. As you'll see when we get to feature engineering, sometimes we want to do multiple things to a predictor. Like, maybe we want to log general living area and then make that part of an interaction. Like that could be sometimes difficult. Things like that could be difficult using the formula method. Another thing is if doing this formula bit is expensive, like takes a long time to compute, you can't recycle it. So if you use the same formula across like 4 or 5 different R modeling functions, it has to redo that every time, which is a really kind of a silly constraint. I wrote a blog post on this a long time ago. I did some simulations and figured out it doesn't matter how many rows are there, but if you have like on the order of thousands of columns, sometimes the time it takes to the formula method to process that large number of predictors can be a good part of the total model fit time. So like if you have like 10,000 predictors and your model fit with the formula takes like 10 minutes, like 5 of those minutes might have been just dealing with the formula. So in wide data sets, not long data sets, it could be kind of inefficient for some things. And I mentioned that like back here, everything on the left side of the tilde is the outcome, and on the right-hand side is the predictors, and those are the roles. There are some types of data analysis that need more complex roles. Like if you've ever done any random effect modeling or some other things, the number of roles in the basic formula method is very limited. And so that's the result of that is in many packages, they've sort of have their own special formula methodology. Like you don't write the formula very differently, but that formula, let's say for a mixed model, can't be used with like any other modeling package. Or other types of modeling packages. So they didn't really think out the roles for variables too much when they initially did this. You can have a multivariate response where you have multiple Ys, so multiple things on the outcome side, but it's the mechanics of how you do that is like C-bind, and it's really clunky, to be honest with you. The biggest problem with the formula method is not so much related to how the formula method works, is that it's so convenient to use when you end up using a modeling package that doesn't have the formula method. You're really disappointed because it's so easy to use, but not everybody implements the formula method. So again, it's like this consistency problem where you want to try out some new package, but the person who wrote it isn't really an R person and didn't know the formula method existed, so they don't have it implemented. And that can be very frustrating. There's a little bit of a discussion about the -1 at the end of things, or in here. So what that means is if I were doing like a linear model, like LM, in some other types of models, what it would do is it would implicitly add another column to the data, which is a column of 1s for the intercept. So beta not, like in linear regression. Adding a -1 would prevent, well, it would do multiple things, it turns out. But the main thing it would do would stop that column of 1s from being added. So there are some times where, like when X is equal to 0, you want Y is equal to 0. So for example, let's say, like the example I was using when we were talking about this recently is, let's say you're modeling the number of tacos sold versus the number of customers, right? So if you have 0 customers, you can't sell any tacos. So that model should go through 0. And having a -1 in that formula would force that intercept to not be in the model, so it's effectively 0. It's more complicated than that, and we've written a little bit about that. Maybe, Julie, if you could link to like the last, was it Parsnip? The last blog post we did on the new modeling functions, that would be helpful. But the intention of having -1, and also you can do it another way by saying +0. So either +0 or -1, the intent there is to not have an intercept in your model, although it's a little more complicated than that. So what happens when you don't have the formula method? Typically, people use something we usually call either the non-formula method or the XY interface. And what you would do then is the modeling function, whatever it is, would have like an argument for the predictors and an argument for the outcome. And so you'd have to give it a data frame or a matrix, depending on what the package wants, that just has the X variables in it, the predictors, and then Y typically is usually like a vector. This is theoretically faster because it doesn't have to process the formula, but you lose all that nice stuff. So you would have to manually make interactions or transformations or dummy variables. So I mean, it's more efficient than the formula method because it doesn't really do anything. It's like it's just offloaded any of that stuff that you needed to do to your code rather than doing it internally. I find it frustrating when people don't have the formula interface. And there are some well-used and well-known R packages that don't have that. And generally speaking, this is what you would have to do. We've kind of solved this problem, as you'll see with Parsnip in a minute. But like an example is LM. Like if I'm going to do some fancy feature engineering thing, LM only has the formula interface. So if you've already done that, like you don't have to like redo it in the formula. A counterexample would be something like glimnet, where glimnet does not have a formula method. And so, again, if you have neighborhood in your model, just using the glimnet package directly, you'd have to do all that work to get the predictors to be in the right encoding and format and all that stuff. So, yeah. So this does happen quite a bit. We'll talk about recipes hopefully tomorrow, as like a third interface to models that's kind of like the formula, but like amped up. So that's another way of doing it. All right, so let's just go back to like an actual model. Let's say we're fitting linear regression. We want to log our sale price, put on log 10 units. And then we have longitude and latitude for these data. So we can just do a simple model fit with longitude and latitude versus the y-axis here. I don't want to like insult anybody like in terms of like, well, that should be obvious, but I do have this question come up every once in a while. It's important to remember that this is a symbolic formula, that you're not actually adding longitude and latitude. So you're saying longitude is a model term and also latitude is a model term. You're not generating one term that is the sum of these two variables. There's a way to do that, but it's not literally. It's not literal, it's a symbolic interface. So, what comes out of here, we've probably all used LM. What comes out of here is a LM object that has all sorts of methods. One thing I'll alert you to is the Broom package, if you've never seen it before. Broom has a lot of convenience tools. We'll talk about the tidy method in a little bit. It has something in it called augment. And what augment does is it sort of mirrors what you would probably do in basic data analysis, where you probably want to compute residuals and fitted values and then plot them. And so if I take my LM model and run the augment method in Broom, I get a data frame back that has the outcome in the units, like the transform units. It has the original data. It also has things like the predicted values, residuals, and so on. So actually, the residuals are here. They're standardized residuals and so on. So if you're doing something really simple, this is a nice method to very quickly get to these quantities you might want to put into a ggplot or something. Let's see. Okay. So if we look at like the top two rows of that data set, it's our training set. Here are the transform data, the predictors in the model, and then these other things. The tidy method is really, really great. The tidy method gives you, and it's not implemented for all models, but it usually gives you back something in a format that you prefer. So if you just wanted to get the coefficients and their standard errors and p-values and things like that, maybe you're going to do a plot of them. There's a summary method for LM, but the problem with the summary method is it gives you a matrix back, The model terms are in rows, row names. So you have to extract them. So you first have to convert it to a data frame, but extract the row names and put that in a column. Also, the column names are not valid are like column names. So the summary method, like one of the columns for the p-values, like PR, so for probability, like bracket T greater than something, and it's not like a valid column name. So like when you make a regular data frame at it, it like changes that name because it's not valid. It's just really difficult to work with. So when David Robinson wrote the Broom package, what the tidy method does is it gives you back things that you probably want from that model in a standardized format that you can use immediately. So instead of getting a matrix back with row names, you get a tibble back. There is a column that's always called term, which has, the predictors in it that were in the model. Estimate is the parameter estimate. Instead of giving you that funky probability less than blah, blah, blah column, it's just called p-value. And again, you can standardize these column names across all sorts of different models. So we're going to be using this quite a bit. It's extremely helpful. And God bless David for doing that. It's been a huge improvement. One other thing that Broom does, it has a method called glance. And glance is like a one-line summary of the model. There's more output here than what I could show on the slide, but the first three columns of glance run on an LM model gives you like the R squared, the adjusted R squared, and sigma is the root mean squared error. So it gives you like performance estimates. It gives you things like the number of data points. It's like a one row with many columns of like summary methods for that particular model. And that, again, is very helpful to quickly get results. Okay, so this is all like base R stuff, like directly going to LM, coming up with a formula, having it encode it, and do all sorts of different things. I mentioned sometimes that the modeling function doesn't have the formula method, and so on. So one thing that we did is we came up early on with this thing called the parsnip package. If you were comparing tidymodels to Caret, what parsnip does is it's sort of the part of Caret that gives you like the same interface to all the models. So the thing is, your interface to LM would be different than the interface to GlimNet. And if you were fitting like a Bayesian model using Stan, the interface would be different than that, and so on. So what we did is we said, what parsnip is going to do is, the first thing you're going to do is say, without any data, say like, well, here's a type of model that we want to fit. Let's say we want to fit linear regression. And that means we're going to have a numeric outcome, and the model is going to be like slopes and intercepts. So there's a bunch of different ways you can fit that, both from the software perspective and from the statistical perspective. So if you're using like regular old ordinary least squares like LM does, well, LM can do that. So can Spark. So if you have like a Spark table, like it's the same estimation routine, it's just the syntax is different. Keras can do the same thing. So instead of it being a deep learning model, you can just make it run a linear regression model and get the same answers as LM would give you. So what we wanted to do is we wanted to generalize, like, how do we allow you to fit the same model using different tools? So so we wanted for you to not have to worry about whether it's LM or TensorFlow or so on. So not worry about the software interface. That's part one. The other part that we wanted to generalize to is the way you estimate those parameters. So linear regression, slopes and intercepts. Ordinary least squares is what LM uses, but you can do Bayesian estimation, which is actually a different way to estimate those slopes and intercepts. And you could use, let's say, Stan to do that. So you wouldn't get the same answers as LM would give you, because it doesn't give you the same answers, but the format of the model is the same. So again, it's just slopes and intercepts. Another example is GlimNet, which is, we'll talk about it more when we get into the actual models, but it's a way to do this thing called regularized regression, using the lasso as a modeling method, or the ridge regression. And so again, it's another way to get different ways of answering, or different ways of getting estimates of the same parameters. It's using a different estimation method. So what we want to do is we want to start off with like, what kind of model are you using? And that's called the model specification. And then you can see that the combination of the software and the method of estimating the parameters is something we call the engine, like the computational engine, okay? So let's say we wanted to fit the same linear model we just fit using LM. The first thing we do is to create a model specification. So we would just say linear regression. So the parsnip function that says we're doing some type of linear regression is just called linear reg. And when you print it out, I mean, you didn't give any data, and you can't give any data. So all it says is, hey, yeah, we're doing linear regression. I don't know how we're going to do it, but that's what we're going to do. And then there's another function called set engine that says, well, how are we going to do that? Like, before we get any data, exactly how am I going to fit this model? And if I say LM, that means we're going to use the LM function to do it. It also means we're going to do ordinary least squares. So then if I print that specification out, then it's the same, but it says, oh, here's how we're going to do it. And then what I can do to actually fit the model is use a function called fit, give it the model specification. I can give it the same old formula I had before in the data, and I can basically get the same LM model. Okay. So what this code here does is kind of replicates this code here. Now, you might look at this and say like, well, that's great, Max. I could do this all in one line before, but now I have to do 1, 2, 3 things to get here. Like, why should I use this? The benefit to doing this is we've generalized everything. So if you've already have your X's and your predictors already configured and all that, and you want to use the XY method, well, LM can't do that, but fit XY is a way to use the same model specification and then use a different interface to fit that model. So it's still running LM. You still get the same parameter estimates you did before, but now if you feel like you have to use the XY method, you can do that, whereas with LM you can't do that previously. Now note that I had to log my data here to do it because I don't have the formula method to tell it to log. So I had to do some things, a little bit of stuff beforehand, but generally speaking, I can use XY now. And the reverse is true. GlimNet only has XY, but it doesn't have the formula method. So if I want to fit GlimNet and I want to do transformations and all that, I can use the formula method in cases where I couldn't have before. So it takes away that problem of what interface to the model does this package have? Because you could use either way using Parsnip. So that's like one nice thing about using Parsnip is even with the same model, you could use formula or not formula method, and you don't have to care about what the underlying code looks like. Now, what if you want to do something else besides LM? What you could do is you could use a separate engine. So instead of LM, you could use, let's say, Stan, and then you can use the same, this is basically the same fitting code as I had before. The only difference is I have a different model specification here, and then it goes off and does all the Stan stuff that it does. And so you can see like I get a Stan fit. In this case, the estimates are pretty close because the default priors for Stan give you that. But I didn't have to like write a bunch of Stan code to do this. Another aspect of it is there's some parameters I might want to give to Stan regarding how it does the Markov chain Monte Carlo, and you can pass those options in here, so they're built into the model specification. So we can add options to our model fit here. We're not constrained from doing that. The point of this is we can fit like the same model across different modeling packages and also across different estimation methods, and our model fitting parts don't change. Like this part will change because it has to be different because the definition of the model is different, but the fitting part doesn't matter. And I could have used XY here if I really had to. So it sort of generalizes all that. Also, what happens if I want to fit a completely different model? So let's say I want to fit a k-nearest neighbor model now using the the KKNN package, which is the one we recommend, instead of using linear reg, I have a completely different structural model. So in this case, I use the nearest neighbor model. This particular model could do both classification and regression. So so we tell it the model mode, which is like, how am I going to use this model to be regression? We can tell it how many neighbors to use, and then the engine that it would use is the KKNN package. And then again, this fit code is exactly the same as it was before for LM, even though the models are completely different. So the nice things about Parsnip is you do a little more work on the model specification, but you can extend that work. You do later work, or you do less work later on as you go to fit the model, because you don't have to do anything differently for the fit calls. You also see in a second that we've standardized all the things that come out of these models. And that's also a big deal, that there are some models that even if you're predicting a single numeric outcome, it gives it back to you in a matrix. And so like all your modeling scripts have this like, if y is, as dot matrix y is equal true, or, is true, then give me a vector back. So some of these modeling functions, their interfaces are different, which is a problem, but also the format that they give you the output in is really, really different. And so a lot of the modeling code that I've written over the years is to sort of post-process all the different things that these packages give me, because I always want the same format so I can go easily between models. So again, the thing to emphasize on this slide is we fit a completely different model. The model specification changes, but the fitting part doesn't. That's all the same. So here's a question. I should do like a Slack poll on this. I fit my model in the training set. Should I make predictions on the test set? And hopefully the answer that you would give me is some form of this. From Exploding Kittens, one of my favorite card games. No, like we don't like fit one model and go to the test set. We're going to do that here just to show you how the prediction methods work, but almost always we would get performance estimates from this class of things called resampling methods, and we'll talk about that very soon. So this is to say, like, do as I say, not as I'm about to do. Don't just go predict the test set. But we want to show how prediction works with Parsnip, so we're gonna take that and do that. So we have these rules for Parsnip. When Parsnip makes predictions, we have this like guarantee, and the guarantee is that if the number of rows if you're predicting, let's say 10 new houses for this model, so the number of rows in the data that you're giving to predict has 9 rows. The number of things you get back from predict is 9. And you might be surprised that that's not always the case. There are some modeling packages where if the data has any missing values, let's say one of the houses has a missing longitude, there are some modeling packages that would only give you 8 data points back and not put a placeholder in for that one that was missing. And then you spend a bunch of code figuring out how to make sure that they are lined up. So when you go to merge that data back in with the observed sale prices, you don't know what to do at that point because you don't know which row is missing from predict. So the number one guarantee we say is if n rows are going into predict, you get n results out, and we make sure that that's the case. Another thing is we're always going to give you a tibble back. So even if we're predicting just like a numeric vector, we're going to give you a tibble with that vector in it. And since the number of rows are always the same and they're aligned, they're ordered the same as the input data, then when you get your predictions out, you can just do a bind calls like you would in dplyr to bring your observed data and your predicted values together. And then the third sort of guarantee for Parsnip is that the column names of those tibble are always the same. So when you make numeric predictions, they're always going to be called .pred. And so one of the, it might be surprising, but if you're wondering like why .pred and not predicted or something like that, the problem is sometimes people build models where one of the predictors is called pred or prediction or something like that. And so we usually prefix things with dots sometimes to avoid sort of like name collisions. So if the input data, if we want to make sure that the output column doesn't have the same name as an input column, in the tidyverse, we usually put like a dot before that to make sure they don't collide. So if I take my LM model that I fit with Parsnip and I just predict the test set, what this will give me back is it will give me a tibble back with as many rows as what were in the test set. Then I can attach that new tibble to the test set data. Remember, we log the data going in, so the observed test set data and sale price, the observed values need to be log transformed because the predictions have already been log transformed. And then when I look at that, I have my observed and my predicted together. So the cool thing about this is this output format is exactly the same across all the regression models. So whether I'm using Stan with linear regression or k-nearest neighbors or random forests and so on, I always get the same format back. The names are always the same, and it's very, very predictable, unlike some of the standard package results. Question, getting different results. It would be good if you could maybe in that thread that Julie just started, paste in the code, exactly the code that you used. When we make these slides, they get executed the same way. So I'm guessing maybe the wrong specification or something was used, but Julia could help you with that. Question, you mentioned your findings related to inefficiencies with the formula syntax. Does this inefficiency carry forward into Parsnip? If you're just using Parsnip, it has the same problems. So if you use Parsnip with a formula and the underlying model takes a formula like LM, what Parsnip does is just captures that formula and just gives it to LM later on. So yeah, we have ways around that with recipes and some other stuff. So basically the formula method in base R, LM and all that stuff uses an underlying function called model.matrix. And model.matrix is really good in a lot of ways, but the way it stores relationships between variables is really, really inefficient. So let's say I have 1,000 predictors. What it stores is it stores a matrix that is 1,000 by 1,001. And my recollection is what that matrix does is it tracks the relationship between model terms. So let's say I have let's say I added an interaction between longitude and latitude. There would be off diagonal entries of the rows for longitude and latitude that have a non-zero result. So it does things like it tracks like which model terms contain the same variables and so on. So the reason I'm telling you this is constructing that matrix can be a little bit expensive, but parsing it and using it for predict and things like that can be really expensive. And the thing is, that matrix almost always has like 99.99% zeros. So the model object ends up being really large and hard to process, whereas like a sparse matrix representation of that same data would make it a lot faster. And so I've actually talked to a lot of people in our core for like 2 decades about maybe updating how the formula method or the model matrix stores that particular matrix because it's really inefficient. And the person I thought that was most likely to make the change has decided not to make it. I mean, I kind of respect that in a way because like every single data analysis script everywhere has something that uses a formula method. And I could see they might be really apprehensive about changing something as like something as ubiquitous as that. But that's the underlying problem is how it stores the data in that formula object. And so Parsnip itself does the same thing. Now stuff we'll talk about maybe tomorrow or maybe next week on Wednesday does not have some of those same issues. So there are ways around it. if you're in that situation, and let's say your data is mostly numeric, the thing I would suggest doing would be either to use a recipe or to just make XY and use the XY method and avoid the formula altogether. That would be my suggestion. So yeah. So we have ways around it, but none that just directly use parsnip. So if you could prompt me when we get to like feature engineering and stuff like that, we can talk about that then. All right. Where were we? We're here. So that's what parsnip does. To show you how to compute performance, we're going to use another package called Yardstick. Yardstick is a package that has all of our functions that do like performance estimation, like accuracy or RC curves and things like that. Most of the Yardstick functions take a data frame as input, and then you tell it what columns are the observed data and what the predicted columns are. So for example, there's a function called RMSE, which computes the root mean squared error. RSQ is R squared. There's one called accuracy for accuracy, and so on. A lot of times we want to compute more than one metric. So what we can do is we can use this thing called a metric set that says like, well, here's some regression metrics that we want to compute for the same data set predictions. So if I want to compute RMSE, R squared, and this thing called the, what's the name of it? The correlation concordance coefficient. I think it's like a combination of R squared and RMSE. You can do all that at once. This gives you a function back that you can call. So this is a function. When you call that, you pipe in basically the data set, and then you tell it which columns have the actual real outcome data in it, and then where your predictions are. And then what it does is it gives you back a sort of a tidy representation of the performance results. So as you add metrics, those get stacked in rows, not in columns, and that makes them easier to work with. So if I take the same model fit for LM, and I want to get the RMSE, and I run this metric set back, I get a tibble back that has a column called dot metric, which tells you which metric it is, how it was estimated. For regression, this is almost always standard, but we'll see in classification there's other things that could be here. And then estimate is actually what the value of the metric is. So our RMSE value from this model is 0.155. That's in log 10 units, which is a little bit hard to conceptualize. It's not a bad model fit for this data set. The R squared is not great. It's about 18%. So maybe I just contradicted myself. It's a concordance correlation coefficient is the name of this, and it's a little bit higher than the R squared, which is good news. So anyway, so as we go through the code, we'll use these metric sets to be the thing that we'll use to measure performance. And again, they take the data frame as an input, and then like in a tidyverse way, a specification of what the observed data are and what the predicted data are. Any questions about that? Okay. I know it's probably likely that like 5 hours from now, you'll be eating dinner or something and be like, oh, I should have asked this. So again, like off time when we're not in here, if you think of anything, please put it in Slack, and then we'll spend time tomorrow going through any questions. So I'm going to go to part 3, which is all about feature engineering. So we have like 20 minutes, so we can get a start on this and then follow it up tomorrow. It would be helpful, I'll just post it in general and you can respond. Am I going at the right speed? So you can thumbs up, thumbs down to that based on how you feel this is working. Okay, that's good. Confirmation bias, maybe, but yeah. Okay.
How about if I set up a poll? I'll set up a poll that's like, should we go faster, same speed, slower, and let people vote? How about that?
Excellent.
I'll just set up that poll.
Cool. All right. So feature engineering. What do we mean by this? Here's if you're running along with the code, this is the code that we'll need that we've already used for this section. So you can think of the thing is statisticians are not good at naming things. So a statistician would call this like pre-processing. It's like how do I make the columns for my data that are going to go in the model? That's not nearly as like cool sounding as feature engineering, I'll be honest with you. But what feature engineering encompasses is really like a couple of different things. In general, you could say like feature engineering is the things that we do to our predictors. It's almost always our predictors to make them more effective in the model. And so that could be a couple of different things. You might do transformations of your data. So you might like log general living area, or you might do like, we'll talk about principal component analysis in a little bit. You might, instead of using the original predictors in your model, you might use the PCA components instead. So that's like a transformation. You might encode your data differently. So if you think about neighborhood in a linear regression object, you need to change the factor column of neighborhood into a bunch of, usually you would make them into a bunch of 0, 1 indicators for the neighborhoods. So that's like dummy variables. So you might like organize your data or represent your data differently than it originally looks like in a way that makes it better for the model. Another thing that we talk about in terms of feature engineering is getting rid of predictors. Like if you have two predictors that are almost 100% correlated, there's really not much point in keeping them both in. In fact, keeping them both in might do harm to your model. So there's this question of like, should I get rid of redundant predictors? And that would be another aspect of feature engineering. So that's like the statistical part of it. Some of this stuff is required by the model. So like LM or linear regression can't take non-numeric data. So a requirement for using that model is to make indicator variables or dummy variables out of neighborhood, right? Another example is if you're using k-nearest neighbors with longitude and latitude. Well, let's say you're using k-nearest neighbors with some numeric predictors, and let's say it's longitude and latitude and pool size, which is in square feet. So when you compute a distance metric, all those predictors have to be on the same scale. And if they're not, the square footage of the pool might have really large values compared to longitude and latitude. So if they're not on the same scale, the distance metric doesn't work well because they're different units, and they, generally speaking, need the same units. So there are some modeling methods that make you do feature engineering or pre-processing because they require certain things of your predictors. So that's one aspect of feature engineering. Another one aspect of it that's kind of independent of the model is more about like, well, what's the best way to represent this data? There are some data sets where it would be better to have the ratio, the ratio of two predictors instead of the original data for various reasons. You might want to put data in percentage form or something like that. Like we talked about location, like do we put it as longitude and latitude or neighborhood or distance to the schools and so on. So, part of feature engineering is really like problem specific because it really is related to the data you have. When we get to regression, probably a week from today, we'll have this data where we have to encode time in our model. So we have like daily measurements. So we can encode that as like day of the year, what year it was, day of the week, what month, was it a holiday? So a big part of feature engineering is to figure out how to take these data and represent them in a way that the model is going to like them, for lack of a better term. It's almost always done on the features, like the predictors. So it's very rare that we would think about engineering the outcome, really. Geez, I just kind of went through this. So again, it could be things like centering and scaling, like to make sure your K-NN model works well, or reducing redundancies and correlations and things like that. So I kind of already went through this. Another thing that I didn't mention is imputation. Most models don't know what to do with data that has a missing value, and so they exclude the row. And so one thing you could do is imputation, where you estimate the value of a predictor that's missing. So if I had a missing, well, here's a great example. Let's say I have a missing longitude and latitude, or I'm sorry, a missing neighborhood value. I might be able to impute it using longitude and latitude. So I'm estimating, in a way, the neighborhood based on other predictors that are in my data set. So that's an important feature engineering aspect. All right, we could probably get through this. Probably the most common pre-processing or feature engineering thing we do is converting non-numeric data to numeric data. And so we'll go back to using ALI again. In the Ames data that we're using, ALI is encoded as gravel, paved, or no ALI access. So no ALI access means it's the same thing as the NAs we saw in the very beginning. So there's 3 different levels of that factor. Those are the 3 possible levels we have. So if we're going to represent that data numerically, how would we do that? Well, typically what we do in the standard, what we call dummy variable or indicator variable encoding method is we take that original column of ALI and replace it with usually multiple numeric columns that are either 0 or 1, depending on the value of ALI. So here are the 3 possible values of ALI in our data. And then we would make, let's say, a column that's 0, 1 for no ALI access based on whether it has no ALI or not. So if the actual data said no ALI access, this column would be 1, and otherwise for gravel or paved, it would be 0. And then we would, let's say, create a dummy variable for paved, which is 0 for gravel, 0 for no ALI, but 1 for paved. So we have 3 different values here, but we only have 2 dummy variable columns. And the reason for that is there's a practical reason for that, and then there's a technical reason for it. The practical reason is that if we know 2 out of the 3 here, we know what the third one is. So to know if it's gravel, we just need to test to see if this one is 0 and this one is 0. So having the third column here that says gravel is really redundant, because we don't need it, because we have all the information we need in the other 2. So it's more efficient to leave out one of the dummy variable columns because we just don't need it. So that's the practical aspect of it. The technical aspect of it is if you were to include all 3 in some models, that causes numerical problems. So remember earlier we were talking about the intercept and linear regression. So the intercept ends up being a column of 1s in your data. And so if I had all 3 indicator variables, if I added those 3 columns together, there would always be a 1 in their sum, and that would be exactly the same as the intercept. And in linear regression, that's called a linear combination, and that actually can make your calculations fail. Ellen knows how to recover from that. It would basically set gravel to be equal to NA. So it wouldn't get a coefficient for gravel. So it knows how to handle it. But the point I'm trying to make is if people don't design the mathematics calculations for these models well, giving it all 3 dummy variables would probably cause a numerical error when it goes to give you your estimates. So the convention is, at least in the statistics literature, the convention is to do a n-1 type encoding where I think there's 28 neighborhoods in the data. So instead of getting 28 dummy variables, we would get 27 dummy variables, and one of them would get left out. The convention in R is which one to leave out is to use the first factor level is the reference cell, and that's the one that gets excluded from the model. So typically, unless you tell it to do otherwise, the factor levels are arranged alphabetically. So gravel, the word gravel comes before N for no alley, and P for paved. So the reason that gravel didn't get an indicator column here is because it's the first level of the factor. It doesn't really matter which column gets left out. It matters for interpretation a little bit, but the math doesn't really change at all. It's kind of arbitrary which one gets left out. You might have a preference for which one gets left out, and you can adjust the factor levels to do that. But generally speaking, it's not like the math changes based on whether it's the first factor level or the last one. It all is the same. So the formula method in R will automatically make these dummy variables for you. Will automatically do n-1 of them. That's a standard for things. That's kind of what this says. The formula method does it for you by default. Except when it doesn't. So, linear regression needs numbers, but not all models are like that. When we get to tree-based models like cart or random forest, they don't use dummy variables. So when you use the formula method for some of these functions that don't need dummy variables, they do everything that the formula method does except to make dummy variables. So this is a known thing. It's generally a good idea that they don't make dummy variables, but I get a lot of Stack Overflow questions about wait, why don't I have a random forest term for neighborhood of North Ames? It just says neighborhood. And so the interpretation and the structure of the results, depending on the model, changes, but those models didn't need dummy variables to begin with. So they're doing the right thing, but it's just a little bit of inconsistency between models in terms of whether it generates dummy variables or not. That said, 99% of the methods you use in R, model methods, use dummy variables. So it makes them for those. You have to opt out of making dummy variables. It always does it unless you code it in your modeling package to not do it. So I'm going to stop here because the next set of slides sort of go all together, and I don't think I'll have enough time to do it well. Let's see. Question. Is there something special you need to do in order to deal with all the levels of factor that are not in the training set, but are in tests in new data, or vice versa? I always end up writing a terrible function to make sure, but I must be doing it wrong. We will cover it, but I can tell you basically. So what the formula method does is, let's say there's a house in Ames that has an alley that is stone, like flagstones, right? Like I lived in Richmond, Virginia, all the alleys are flagstone there. So there's a new value. So like in a new house, that data would come in with a value of flagstone. So, but you don't have any dummy variables for that, right? So the first thing that would happen is if you're using model.matrix, it would give you an NA value for that. Because it doesn't know what to do with it, because it doesn't have anything, it doesn't know, when you make dummy variables by default, the default way to do it, there's a menu of things it could be, and you give it something that's not on the menu, and and I think it does the appropriate, I don't know what to do, it doesn't fail, but it gives you an NA value back for that. I think with a warning, and Davis knows this, and I don't remember, you can tell me if I'm not getting the details of that right. So if you're using the standard infrastructure, it literally just doesn't know what to do. We have ways in recipes that we'll talk about tomorrow of handling that. So what we can do in recipe is there's a way to do a novel category. So if I think that there might be more alley types on the way, there's a recipe step that we can add that will add a future level when you fit the model that says new value or something like that. So you would have instead of having these 3 factor levels, you'd have a 4th level that says new value. And then when you get new data to make predictions, if you have an actual new value that's not gravel, no alley, or paved, it knows to lump that into the factor level of new value, and then it does everything the way it's supposed to do it. So we have other ways of handling this where we can pre-allocate like a level to handle things if you think you're going to have new values. Now, if you fit a model without doing that, there's really not much you can do about that. You kind of have to pre-plan. We won't, so there's some other options. We won't talk about this much in detail tomorrow, but there's this method that I don't really like, but it'll work for you, called feature hashing. What feature hashing would do is it would create dummy variables not based on the list of the ones you know about, but the actual values in the like gravel or paved. So so what it does is it can create dummy variables based on the actual text that's in here, and so that can handle situations where we have new values. In a really low dimensional case like this, where we only have like 3 values, that would be a really bad way of going about it. But like, think about like if you have a data set that goes across different states, and you have like city is one of the predictors, and there's hundreds and hundreds of cities, let's say, across different states, and a new city pops up. This feature encoding, feature hashing method would be good in those situations. And so that's a method that would be able to handle new values, but it does that because it operates completely differently than dummy variables do, like the standard dummy variables do. If you want to, so if you go to bookdown.org /max/FES, or let's see, you should be able to type feature. So feature engineering and selection is a book we wrote last year, and that should lead you to the Bookdown version. Yeah, so if you do that, you'll find an ad for it, but in the book, we have like a section on this. So when we talk about encoding categorical data, we have approaches for novel categories. So let me put that in the Slack channel here. So if you want to know how this feature hashing thing works and when it might be useful, you can do it in a recipe, as we'll talk about tomorrow. But there are other ways of dealing with this that we don't really go into in the class. Okay. Next question. You might be covering this tomorrow, but earlier you talked about having a data set with hundreds of columns predictors. What's your approach to feature engineering in the scenario, or even effective EDA? Yeah, that's a great question. The areas that I've worked in where I have like numeric data with that many predictors, they are almost always correlated. So just to give you an example, I was talking about like drug discovery. Computational chemistry can take like a drug and calculate things like the number of atoms in it, or the number of bonds, or the number of like carbons in it. There's all these like analytical calculations you can do on a drug to get predictors for your models. But the thing is, like, the number of atoms is highly correlated with the surface area of a molecule, which is correlated with 100 other things. So in all the places I've worked where I have a lot of predictors, whether it's in biology or chemistry and some other things, they're usually really, really, really highly correlated. So we'll talk about principal component analysis tomorrow. That's the place that I typically start. I typically start by saying, like, all right, let's see how much redundancy there is in this data. You can do that through like a correlation matrix or some other things. But the first thing I would say is like, well, how much are these things similar? Like if I have 1,000 predictors and they're all telling me different things, that's really interesting and that's really important. I think most of the situations I've been in are where, like, even though you have 1,000 things, they're measuring maybe like 5 underlying real like trends in the data. So they're like overdetermined, where, like, you know, like I was talking about, like size of a molecule. You might have like 150 predictors that represent that in slightly different ways. And those differences might be informative, but their correlation between those things might be like 0.9 at the minimum. So the first thing I typically do is I use principal component analysis to start making plots of the data to see, like, are there rows of the data that look really different than others? Or I look at like the correlation matrix and see like, oh, these things are really correlated or they're not really correlated. Another aspect where this happens is in like natural language processing and text mining, where you do like a bag of words type thing, where you have like, potentially millions of words and you chop them up in different ways into 0, 1 kind of indicators for these things. And you could do similar things to what I just mentioned, but there's other ways that are specific to text that would be relevant. And maybe Julia could put a link into her book that she's currently writing, because how you would do that with text is very different than how I would do it in other places. So one other thing I've done, and I've done this quite a bit, is I will write a loop that has a maximum of like 100 iterations, and I will randomly sample columns of my data and just do scatter plots of them, just to see like, okay, when I randomly select 2 columns and do a ggplot, what does that look like? Am I seeing the same trends? Am I seeing like outliers? Or are they always the same outliers? Like literally looking at your data cannot be overemphasized. So I typically like try to do as much of that like actual observation of the real data points as possible. Even if it's like a random selection, and maybe I'll probably only get like 1% of the actual combinations. But again, if there's a lot of correlation, you're probably covering a lot of ground by doing that. So that's something that you can do. Okay, so Davis. Okay, so I'm going to stop there. I'm already 4 minutes over. We'll reconvene tomorrow at the same time and start on infrequent levels of categories. Again, please, I know I've mentioned it a couple times, seed any questions that you have tonight into the Slack channel. And also, you can do it on the regular Slack channel or Slack us, or Slack me individually. Like if there's things that you're not happy about, like how this is all set up, if there's anything, like we want to get feedback as much as possible. So don't be afraid to give us feedback, whether it's on the channel or just to like DM us on Slack. Because day one, so we can change things that are really bothering people. So any last real quick questions? So normally this is where we go to Rye House.
Yes, and yes, that would be nice. I do miss the trips to Rye House. I look forward to being able to do that again with you and the whole crew of people learning. And that's, you get a lot more learning done there. A lot of good insights come over whiskey.
Yes. Okay. Well, I will end the set. Anything else, Jared, you want to say, or should I just end the session?
I think one of the last key takeaways was to about anything you don't like is what he just said to do. Whether it's about his past life, Max is there for you to talk about what you don't like. But aside from that, yes, hope everyone had a great first day. I thank everyone for coming. I also thank Max and Julia and Davis for being here, providing this education. I've seen Max teach this at least, might be in the double digits now, and I always get a little something out of it every time I see it. A friend of ours said this is like going to a Deadhead concert, a Grateful Dead concert. And I'm like, yeah, we're making a bootleg too. So I'm very excited. I learn something new every time I learn from Max. So thank you. And thank you everyone for enjoying, hopefully. Well, I'll see you back tomorrow at 1 o'clock for round 2. Then after tomorrow, it'll be the following Wednesday and Thursday. So see you all tomorrow. Have a great evening or sleep, depending what time zone you are, or afternoon, depending what time zone you're in. I think we have people from Europe, East Coast, and West Coast. So everyone have a wonderful time of day.